So how many people are from MHC background? 5. And anybody who is from GIET? Okay, so I think you are from GIET electronics engineering, right?
Yes.
Okay. So can I see the slide? As you can see, the title of my talk is Structural Modified Fiber Optic Sensor based on nanomaterial coatings. So if you see the title, so it consists of 3 parts, right? The first part is the fiber optic sensor. The second part is the modified, structural modified, and third part is the nanomaterial coating. So what I will try to explain maybe in the next 1 hour is to give you an idea about how this optical fiber sensor can be improved in its design based on its geometrical structure. And further, you will see how this sensor, fiber optic sensor, when it is modified, can be further improved by using this nanomaterial coatings. So fiber optic sensor is in fact not a new concept. But what I will try to explain is how we can modify this conventional optical fiber sensor based on its geometry and based on the different nanomaterial coatings. So this is what I will try to explain maybe in the next 1 hour. Now, coming to my talk, this talk is not based on mathematics. In fact, I will try to avoid mathematics. So I will use minimum mathematics here, but I will try to give you a feeling that how this sensor can be designed based on this geometrical modification and based on this nanomaterial code. And I will feel interest among yourself how this sensor can be used in day-to-day life. So this is what we will try to understand maybe in the next 1 hour, and this is the plan of my talk. And as I was mentioning during the inauguration, there is a center at Gunupur University, which is known as the Center of Excellence in Nanoscience and Technology for the Development of Sensor. This is a center which you have started in 2018, getting the fund from the Department of Higher Education. And I will say something about the center because as I observed that some of maximum of your students, and I will take some time to explain about my center, and then of course we will explain why we will do something research in fiber optic sensor and the basic principle, why nanomaterial coatings will be used, why the structural modification is made, and finally we will see what are our important contributions you have made in this fiber optic sensor. And this is about this center, and you can recall yourself, as you can see here, this is the center we have started in 2018 December, and the main objective of the center, you can see here, to develop low-cost optical sensors for healthcare, food security, and environment. So we are trying to develop some low-cost prototype for applications in the food security, environment, and healthcare. And also, in this process, we create experimental facilities to train these faculty members and researchers, particularly who are working either in the nearby universities or in different colleges, right? And obviously, we want to establish the networking and scientific collaboration with the reputed institute in this process. And the last one, the publication, create new idea, arrange for something. This is actually obvious because otherwise this center will not sustain. You have to arrange funds for our center because the center is funded for 5 years, 2018 to 2023. Of course, this project will be over by 2014 March. So we have to see how to generate fund for the sustainability of the center. So this is about a center, the Center of Excellence for Nanoscience and Technology for Development of Sensor. And
yes, sir, there that remote you can access. So that remote what you have in your hand, you can
know that.
Welcome to the Center of Excellence in Nanoscience and Technology for the Development of Sensors, CONSTES, at Gunupur University, Odisha, India. In this center, groundbreaking research and innovation come to life. In this short video, we will introduce you to three remarkable low-cost proof-of-concept prototypes that are revolutionizing different fields. Our dedicated team has developed an affordable and efficient method to detect HbA1c levels, a crucial indicator of long-term spectrum in diabetes. To meticulous research, we have proposed a method that utilizes a digital holographic microscope for average phase measurement of RBCs. This method offers accurate results without the high costs associated with traditional methods. Next, our journey into nanocomposite materials such as zirconium supported on magnetic nanocomposite and magnetized retrievable graphitic carbon nitride supported zirconium straight nanocomposite for treating industry influence. Specifically, those contains dyes. By harnessing the power of nanotechnology, we have engineered an innovative solution to remove harmful dyes from wastewater. Our material not only contributes to a cleaner environment but does so economically. Our commitment to healthcare and agriculture has led us to develop a groundbreaking fiber optic sensor. This powerful yet affordable device holds the potential to revolutionize healthcare applications by accurately detecting albumin, acetone, cyanic acid, nitric acid, mercury ions, and lead ions. Additionally, our ongoing research focuses on low-cost sensor solutions to aid farmers in optimizing crop growth. In brief, we have given a glimpse of the work happening in our Center of Excellence. These low-cost prototypes in HbA1c detection, nanocomposite, and fiber optic sensor are poised to reshape industry, enhance lives, and create a significant impact on our society's economy. Thank you for your patience. For more information and collaboration, please contact us at website www.constts.org.
So this is in short, in fact, a short video we have prepared for us to give a feeling what we are doing at our center. This is my team, and as you can see, this team is not only from physics, but from other departments, from the Department of Chemistry, from the Department of Biology, and recently also we have included some faculty from members of the Department of Geography. This is completely a multidisciplinary research. Because what we are doing in our center is starting from the scratch. We are starting from the materials and then we are ending up with some prototypes. So in this process, you have to take the help of different people like material physics, chemistry, biology, because we also do some sensors based on healthcare. So you have to also take the help of the biologists. And finally, the computer science and also electronics, because you have to write codes and you have to develop these prototypes. So this is basically a multidisciplinary research center, and this is as Dr. Galai was mentioning. To use this center. In fact, these are the activities we have created so far in the center in the last maybe 4 to 5 years. So we have a simulation lab and different softwares. You can see the different softwares which are available in this center. Console, multiphysics, SAFOS. This is a in-film simulator and quantum X-ratio. These are the softwares which are available, and these softwares are in fact remotely connected to the server of IoT Physics, Institute of Physics. So some softwares otherwise will not run. And these are the softwares which you use to get some personal information about these materials. Now, as I said, our aim is to develop some sensors based on the material coatings, basically the nanomaterial coatings. And therefore, you have to first see whether the particular nanomaterial which you are thinking will work for a particular application or not. So for that, just you cannot go to this lab to prepare these nanomaterials. So for that, what you do is you have to go to the simulation lab and you have to see, you have to investigate whether this material you are thinking for the coating on this fiber optics will work properly or not. So for that, these softwares are used. Basically, you are using quantum X-ratio. Sometimes you also use console for this, to know whether this material if you are thinking for a particular sensing application will work or not. And of course, SAFOS is not used for that. SAFOS is used for solar simulation, particularly for hard relations for solar cell simulation. So basically, we use these softwares to know whether the material you are thinking for a particular use will work or not. Now, once you have decided that yes, this material is working fine from the simulation, then you go to this nanomaterial synthesis lab. There is another lab where you can prepare these nanomaterials and prepare this nanomaterial as per this simulation result. And once you have prepared this nanomaterial, then you have to see whether this nanomaterial will work or not. For that, you have to go for this nanomaterial characterization lab. So where you can characterize these different prepared materials, and if this material is working fine, or if the material will give its properties that you have decided, then it is okay. Otherwise, again you have to go back to the simulation lab, and again you have to design your own material. And this process will continue till you will get a suitable material as per your design specification. Now, once your material is found that yes, this material will work for a particular sensing application, then you have to go to the sensor design lab. So there is another lab where you can design the sensor. You can take this optical fiber, then you have to pour this material, and then you have to test whether it is working for a particular sensing application or not. So these are the different labs that you have right now. Simulation lab, nanomaterial synthesis lab, nanomaterial characterization lab, and sensor design lab. And this is particularly for those students who are doing MSc or also for the BTech in electronics communication. And about this achievement of our center, as you can see, of course, we have published many journal papers, and this is how we can see our achievement in terms of publication. For example, here, and these are the prototypes that you have actually produced in our center. The first one is, as I have mentioned, is a low-cost digital holographic microscope based on SQ1C detection. So this is basically a low-cost prototype where you can measure this SQ1C level. If you remember when I came here last time, I was giving a talk on this low-cost holographic microscope for accuracy detection. And now this equipment is ready, and the equipment now we are trying to, the patent is over, and now we are trying to, sell this, patent to some industry so that they can manufacture in this large scale and can be used by this society. The beauty of this prototype is that, why SQ1C is matter? This is actually to monitor the blood of the lab. So if you want to monitor your blood glucose level for last 3 months, for example, then you have to measure HbA1c level. And currently, you are using an instrument which is called HPLC, whose cost is not less than 10 lakhs. So therefore, ordinary pathology center, they are not, keeping this equipment because the cost is very high. But if you talk about this, cost of this particular prototype, this is only 40,000. So just make a comparison. The HbA1c equipment which is used nowadays is around 10 lakh, and the cost of this equipment is around 40,000. So that means ordinary pathology center can use this, or they can afford this equipment and can find the HbA1c level with low cost. The second one is another prototype which is basically for treating the industry effluent. In fact, the research is again also interesting. The history is also interesting because there is a industry called IRB, Indian Rare Earth Limited, which is near to Gunupur, near to our university, and they have actually suggested us to make something from this waste of their well, in fact they are producing this for the zirconium phosphide. So zirconium phosphide is a waste which they are releasing to the sea, and this zirconium phosphide is poisonous. In fact, when this zirconium phosphide will go to the sea, then it will affect this environment. Right? For example, the fish will take that zirconium phosphide and it will eat the fish, and therefore ultimately it will cause health hazards. And they say that when you take this zirconium phosphide and convert this zirconium phosphide to something which can be usable, because as of zirconium phosphide they are releasing to the sea, then we took this as a challenge and we have converted it to zirconium phosphide to a nanocomposite which you can use to treat the industrial effluent. Now, industry effluent basically contains dyes, and by using this material nanocomposite with this zirconium phosphide, in fact, we use zirconium phosphide to prepare this nanocomposite, and this nanocomposite can be used to treat this industrial effluent. So this is how you have converted this zirconium phosphide to a usable material. In fact, they are releasing this zirconium phosphide to the sea, and in this process, the environment is polluted. So this is what we did in the second, pattern. Third pattern is something related to this website. In fact, we have designed a website where you can take this light out and in as per your requirement. This is particularly useful when you will go for sensor design. So this is the third one. And the most recent one, which we have not patented, but I have shown here, is another prototype where you can measure this HbA1c without breaking blood. So, if you want to measure HbA1c, you have to stick your finger and take blood, and then you have to measure what is the HbA1c. But recently, you have also designed one prototype. This is just like a you are measuring this substance level oxygen. So you just put in that chamber, then immediately it will give you what is your HbA1c level. So this is the recent prototype you developed. It is under testing, and I think we will go also patent for this non-invasive finger glucometer. So what we are saying all these things is we will find that we are trying to develop some low-cost prototypes. They are compete with the others in developing high-cost prototypes. So therefore, our intention is to get some prototype, low-cost prototype, so that this ordinary man or the society can use those prototypes for their use. Okay, then let us on to this talk. As I say, my talk is something related to this biomedical sensor. So let us try to understand why you will do a research in this fiber optic sensors. So for this, I have shown here the national and yes, the current research on fiber optic sensor. So if you see this, you can understand this market size of this fiber optic sensor in 2021. This is 2.12 billion, of course, USD, right? And the market size in 2050 is expected to 7.1 million USD. That means there is something interesting, and also you will get money if you will do some research on this fiber optic sensor. Because the market strength is there in this fiber optic sensor, and this is the reason why people are interested in doing fiber optic sensors. Coming to this publication in this, and this is where I have shown this publication. This is the publication in India, and if you see from 2012 to 2022-23, this is 23. This number of publications is gradually increasing, and this is where I have shown for Odisha. This is national level publication. This is the regional level publications, and if you see here, the publication number somehow decreases during this 2012 to 2020. I don't know the reason, the exact reason why there is a decrease in this number of publications in this period, 2012 to 2016, and again 2016 to 2000. There is a slight increase here. Again, there is a downfall in the number of publications. But again, after 2020, this number of publications is increasing, right? So this is the increasing trend in this number of publications. And if you this is of course Odisha, and this is about our publication in this fiber optic sensor specifically. And as I said, we have started this fiber optic sensor research in 2018. But my area of research was something else. But getting a bond in this fiber optic sensor, we have started our research in 2018 December, and this is how we have published in during 2019 to 2023. And as you can see, there is an increase in this number of publications in our group. In fact, in Odisha, there is a limited number of researchers in fiber optic sensors. For example, Rajan is there who is doing some work in fiber optic sensor, and Deepik was there. In fact, Naisar now I think is at IIT Delhi. So the number of researchers, particularly in this fiber optic sensor, Odisha is actually not very. So recently we had a meeting with the director, Naisar, IOP, IMT, and we are trying to have more number of people to collaborate in this fiber optic sensor, and see that this fiber optic research sensor research will increase maybe in the near future. Okay. Now, looking into this audience, I have prepared this slide like this. So let me start with the very basic. And this is actually the basic principle of fiber optic. So you have a source. Basically, you have a source, and you have a detector, and a fiber which is joined between the source and detector. Right. So any fiber optic sensor should have a source, should have a detector, and a fiber should join between the source and detector. Now, if you see the source here, then the light from the source is coupled into this fiber, and finally this light will reach at the detector. And therefore, if you want to measure this power of light received at the detector, this is here P out, and this will change in accordance with this relation. But this P in is the power which is emitted by the source, and this eta is the coupling efficiency between the source and fiber here, and T is the transmission efficiency, and M here is the measurement which you are applying here, and R is something related to this responsibility. Now, we will assume that this P is constant, eta is constant, T is constant, R is constant, then this output power which is received at the detector will be proportional to the measurement M. Now, what is the measurement here? The measurement is the quantity which you want to measure. For example, if I want to measure temperature, then I have to apply temperature here. So the quantity which you want to measure is the measurement. So if you apply this measurement here, somewhere here in a small portion of this optical fiber, then this P out will change. Because they say, if you assume that all these parameters are constant, then the output power which is received by the detector should be proportional to this measurement. And if you see this measurement is a function of different parameters like intensity, phase, wavelength, and polarization. That means when you apply this measurement on a small portion of this optical fiber, either intensity will change, or phase will change, or wavelength will change, or polarization will change. And based on that, these fiber optic sensors are classified. For example, if your output power changes with respect to this intensity, this is called an intensity modulated sensor. Similarly, if your output power changes with respect to phase, then this is called as phase modulated sensor. Similarly, your spectrally modulated sensor, when it changes with respect to wavelength, and polarization based sensor, if its output power changes with respect to polarization. Therefore, the output power which you will measure in the detector basically is decided by a measurement which you apply. And when you apply this measurement, either of these parameters will change, and based on that, this sensor will be classified. This fiber optic sensor will be classified. Now, see, if you apply this measurement, then definitely this output will change. Let us take an example to explain what is the basic principle in more detail. For example, this is an intensity modulated sensor. Means when you change this measurement, what will change is the intensity. So when you will change, for example, different measurement, let us take the measurement in temperature. You are trying to measure the temperature. So when you will apply different temperatures, for example here, then the intensity of this will change. Intensity here will change. That means in the different values of temperature, the intensity we will get at this detector will change. Similarly, for example, you want to measure concentration. So you apply here different concentration, and based on this different concentration, the detector output will change, and then you calibrate between this different concentration or different temperature and the output. So when you calibrate that, what you will get is this. For example, here I have shown the calibration between this concentration and this output. The output is measured in terms of current. Here, this is the photodetector current. So what I have done here is I have applied different concentrations as a measurement, and I have measured the output at the detector in terms of your current. And you can see the graph turns out to be a straight line. So that means a linear graph is to be obtained. If the variation of this output at the detector with this measurement is not a straight line, then you cannot use this as a sensor. So the first and foremost requirement for a fiber optic sensor is that when you are plotting a graph between the measurement and the output at the detector, it will be a straight line. And as you can see here, when you plotted a graph between concentration here is the measurement, different concentration along x-axis, and the corresponding, the output at the detector, it comes to the straight line. And once you got this calibration graph from the straight line graph, you can immediately calculate the different parameters like sensitivity, limit of detection. Of course, you have to also find the specificity and temperature difference, because these are the important parameters which you have to test for the sensor. Right? That means the sensitivity is obtained from the slope of this straight line, and this limit of detection is the minimum value, for example, of concentration here, because I have plotted concentration. Limit of detection will give you what is the minimum value of concentration that can be measured with the help of this sensor. Similarly, specificity, that means when you are measuring concentration, for example, if you are measuring concentration for a particular, let us say, biomaterial, there are also other biomaterials which are present. So your sensor output should not link with the other biomaterial. So whatever biomaterial you want to sense, the change in the output will be only due to that biomaterial, but not due to the other biomaterial. This is what the meaning of this specification. And temperature difference, your sensor, output should not change with temperature. If you change with temperature, then you cannot use this sensor maybe in different harsh environment. So these are some of these basic requirements, and also some of these parameters which you have to calculate when you have to design a particular fiber optic sensor. And these are the different types of sensors. So let me just skip this slide. Just you can see here that the sensor you can classify into intensity and absorption based sensor, resonance based sensors like surface plasmon resonance and local surface plasmon based sensors, and also you can have sensors based on fiber rating, and you can have some interferometric based sensors. And I will now explain about a few of the sensors. I will not explain about all the sensors. Maybe I will explain about one surface plasmon based resonance based sensor, and another interferometric based sensor, and maybe another absorption based sensor. Because these are some of the sensors we have developed in our lab. So I will explain how these sensors can be developed based on this intense absorption, based on the surface plasmon resonance, and based on the interferometry. So this is actually the SPR based sensor. SPR stands for surface plasmon resonance. Now what happens here is something like this. You see, this is your optical fiber, and this is how this light propagates in this optical fiber. And this optical fiber is made out of basically glass, sometimes plastic, which is an insulator or dielectric, right? So this is basically a dielectric, and there is another coating here, which is matter. So this is the matter, and this is the dielectric. So whenever there is a metal dielectric interface, what will happen is there will be a plasmon wave. It will be produced here because this is matter. So a large number of electrons are there, and therefore this metal dielectric interface will give rise to this plasmon wave, right? So the plasmon waves will be here, and when you will shine a light into this optical fiber, for example, in this region, then when some condition is satisfied, that means when the frequency of this plasmon wave will match with this frequency of this incident light wave, then there is a resonance which will take place. So when the resonance will take place, then this is called a surface plasmon resonance. So when the surface maximum resonance will take place, what will happen is there will be a maximum absorption here, and therefore the output will get here, and the output of the detector will decrease for that particular frequency. You can also talk this in terms of wavelength, because frequency and wavelength are related, right? So that means for a particular wavelength of this incident light, there is a possibility of resonance which will take place, and when this recurrence will take place, there will be maximum absorption, and when there is a maximum absorption here, you will see that the transmission here will certainly take place, and this will take place for a particular wavelength or particular frequency. Now, what is interesting here is, suppose I will put a material here, the material which I want to sense. So when I will put a material which I want to sense, then the reality constant here will change. Reality constant of this medium will change. So when the reality constant of the medium will change, then the wavelength or the frequency for which the resonance was taking place will not change. And this is where I have shown, if you will change the concentration of this measurement here, how this resonance wavelength is changing. This is basically a graph between wavelength and the normalized transmission. So as you can see, when you are changing this concentration, then the transmission suddenly decreases at a particular wavelength, or you can also say at a particular frequency. So this is where this resonance is taking place. And when you change the concentration of, or you change this, measurement here, or there is a concentration of some biomolecules here, then this resonance wavelength will change. So therefore, you can calibrate between the change in concentration or concentration and this change in this resonance wavelength. And if this turns out to be a straight line, then you can use this for sensing application. Because it is found that for a small variation in this dielectric constant of this measurement, there will be a change in this resonance wavelength. So you can calibrate between this, change in this resonance wavelength and the concentration. And if it turns out to be a straight line, then I can use this for a sensing application. So this is what we will do for SPR based sensing. In fact, as I said, when you are using an optical fiber, then the first principle which I have explained here is the SPR principle, using which you can realize sensor, fiber optic sensor. And the second principle which you can also use is based on absorption. Now, if you take an optical fiber, basically light propagates in this core. You know that optical fiber is made up of basically a core surrounded by cladding. Of course, other layers are there. The main layers of the optical fiber is a core surrounded by cladding. And mainly the light travels in this optical core, core of this optical fiber. But there is also some light which is present in the cladding. The light which is present in the cladding is called the evanescent field. And this evanescent field is an exponentially decaying field. That means when you go away from this cladding, then this value of evanescent field will gradually decrease. Now, in the second type of sensor, which I refer to as absorption sensor, you will utilize this evanescent field. Now, what you do is like this. You take this evanescent field and allow this evanescent field to interact with the measurement. Now, when it's a measurement, this is the quantity you want to measure. Anything you want to measure, that is called as a measurement. So, in the second type of sensor, which is called as absorption-based sensor, you take this evanescent field out of this core and then allow this evanescent field to interact with this measurement. And if this interaction strength or the interaction between the measurement and evanescent field increases, then the light you will get the output will change rapidly. So this is basically how this measurement interacts with this evanescent field. But the problem here is as I said, the aberration field can only travel a very short distance out of this core. So if your dimension of your measurement, for example, I want to measure some molecule, if the dimension of the molecule is not comparable to that aberration field which is coming out of this optical fiber, then the sensor cannot be designed properly. So therefore, there are some relations using which you can know what is the depth or what is the distance up to which the aberration field can come out. So you have to calculate what is the distance to which the aberration field will come out, and the distance should be comparable to the material coating. Because as I say, when you give a coating, this will have some advantages which you will see it later, but the thickness of this material coating should not be more than the aberration field, that is the distance up to which the aberration field will come out. So, how we define this aberration field? There are some relations, in fact, by which you can calculate this aberration field. Here, I have just shown this distance for the aberration field. Basically, depends on N1 and N2. And if you assume that this is basically made of glass, then this is of the order of this wavelength of light which you are using. So you are using some source, for example, if you are using visible light, for example, 632 nanometer light, then the aberration field for glass fiber is of the order of 630 nanometer. That is, the aberration field will come out of 630 nanometer. Then your material coating should not be more than 630 nanometer. If it is more than 630 nanometer, then the light cannot come out of that and it cannot interact with this one. So this is what you have to keep in mind. That while using this sensor as an absorption sensor, you have to know the distance up to which the field will come out of this light. Sorry, will come out of the core. Right? The second thing which you have to also remember is different types of optical fiber. You know, there are different types of optical fiber like single mode fiber and multi-mode fiber. In single mode fiber, only a single mode will propagate along this fiber. And when you take a single mode fiber, then the aberration field is much more than this multi-mode fiber. Therefore, usually if you want to use this for absorption sensor, optical fiber as optical sensor, then preferably use a single mode fiber so that the light will, the aberration field which will come out will be more. And again, you see, this whether this fiber is single mode or multi-mode is basically decided by the diameter of this N1 and N2, right? In fact, the number of modes which will propagate in this fiber is decided by a number which is called a B number, which is decided by this radius of the core, then the wavelength of this source, and refractive index of core and refractive index of light. So therefore, this number of modes is proportional to that number B, and B is proportional to A, right? Therefore, if you go on decreasing this radius of this core, then you will see that the number of modes propagating in this fiber will go on decreasing. And a situation will come where only a single mode will propagate in this optical fiber, where we call that is a single mode fiber. So therefore, when you will design an optical fiber sensor for absorption sensor, you have to preferably use this single mode fiber. But sometimes also you can use plastic fiber with some changes. Now, this is another slide where I have shown that if you bend the fiber, then also the field which will come out of this core. Because basically my aim is to interact the field which is coming out of this core to interact with the measurement. So therefore, if you will simply change the geometry of the fiber, here I have shown a simple diagram where you can understand that if you bend the fiber, then the amount of field which will come out of this optical fiber will increase. When the amount of light which is coming out of this optical fiber is increasing, then the extent of interaction will also increase with the measurement. So my goal is to see that if I am designing a absorption sensor, more field should come out from this core so that it will interact with this measurement. Then the question is, how I will change the geometry. This is in fact a simple geometry which has shown where you can take more field outside this point. But is there any other geometrical changes that is possible in an optical fiber so that I can take more amount of field outside this optical fiber so that more amount of interaction or more extent of interaction will take place with the fiber and therefore the sensitivity for detection. So this is what I have mentioned in the title, that how to modify the geometry of the optical fiber so that the amount of field which will come out will increase so as to interact with this measurement more and more. And how to do that, in fact, how to change the geometry of this optical fiber, or how to know that which geometry is suitable for the situation where you will get more amount of or light to leak out of this optical fiber. The one way you can do is you can do some mathematical calculations and you can know in fact in which configuration more light will come out. But there is another method by which you can know or you can test different geometrical configurations and you can find which is the best configuration for taking more light outside this board, so that it can be designed as an effective observable basis. So for that, you need some simulation. So you have to use some simulators or softwares where you can design different geometry of this optical fiber and to see in which configuration more amount of light is coming out of this optical fiber. And you use this configuration for experiment. So this is what you could do first. First, you have to design the geometry. You have to modify the geometry. So you take a straight optical fiber and then change the geometry. How will you change the geometry? That is your option. In fact, you can think what should be the change in geometry so that you will get more amount of light which is taking out so that you can interact with this laser. So the first job here is to use some simulation techniques to know the best geometry for the situation where more light will leak out, the more light will come out of this board and will interact with this fiber. To give you a very sensitive design of observation based. So I will show you here some of the geometries which you have actually investigated later. And now suppose I have decided this is the geometry where the maximum field will come out. Then what I will do is I will use a suitable nanometry. The first part is over. That means I have decided the geometry. This is the geometry which I will use for my sensor. And once I have decided this geometry, then I will go for this nanometry. I cannot just take any nanomaterial for my purpose. I have to see what is the material which I want to sense, or what is the measurement which I want to sense. And once I have decided this measurement, then I have to think which material, which nanomaterial I have to put on the design, spatially geometrically designed optical fiber. How do you do that? Again, you have to go first. You have to do some simulation, molecular based simulation, and you have to see which nanomaterial will work for that particular measurement. For example, if I want to measure, for example, CLEKC, this is a bioreactor. If I want to measure CLEKC, then what specific nanomaterial I should put on this specially designed optical fiber geometry so that it will sense that CLEKC only. Because when I want to sense or detect CLEKC, then the nanomaterial should only interact with CLEKC, but not any other material. So the nanomaterial which are saying should be chosen in such a manner that that material should only interact with the measurement you want to measure, but not any other material. Similarly, you have to see that when you are using this nanomaterial and you are changing this temperature, then also there should not be any change in this injector. Otherwise, this sensor will not work. Of course, this range of temperature is not maybe from room temperature to it may go up to 80 or 90 degrees. You may just check whether your sensor is not giving, changing this detector output in this range of temperature from room temperature to 80 degrees and degrees centigrade. So if it is not changing, that means your sensor is very good. So why this nanomaterial coating is used, you can just see here. These are the reasons why you have to coat this nanomaterial: enhanced sensitivity, selectivity, fast response time, right? And how to choose this suitable nanomaterial, identify the sensing application, then understand the sensing mechanism, and then evaluate this nanomaterial. That means you have to decide which nanomaterial will work for this particular application, particular method. And these are some of these, criteria also you have to check: assess compatibility, selectivity requirement, environmental conditions, cost and availability test, which I was talking in the morning session. Cost is also very, very important because when we have developed this prototype and we have, approached to some industry, they ask some questions which you have never heard about some economics, there are this cost impact you have never heard. And finally, when I ask what is the actually reason why you are asking this question, then they say you are trying to understand what will be the cost of the product. So the cost is also very, very important when you are designing a sensor. And this is, and of course, you have to review some existing literature whether this type of sensor or this material that they can earlier or not. If they are taken earlier, then same materials, of course, you cannot take. You have to modify this material, something like that. So finally, you see these are the different conventional geometries. These are not in fact new geometries. So if you have a fiber like this, then this is your core. This is a cladding. Here I have taken out this cladding here and I have rotated this nanofibers or this nanomaterial. So this is a straight fiber where I have taken out this cladding. So clad removed optical fiber. Similarly, here we have a band fiber. This is ordinary band fiber. So when you band fiber, definitely the amount of light which will come out will increase, and therefore it can be more appropriate as a hydrogen-based sensor. Okay, these are the common geometries. Now, as I said, the first thing which you have to do is make simulation and see which geometry will work. And this is where we are trying to understand if I will do certain banding. This is not just like banding as I showed before. This is something like a balloon. So this structure which I have shown is something like a balloon, right? This is something like a balloon. So we are trying to understand if you take a fiber and bend this fiber in the balloons are bending, then how this light is leaking out. Similarly, you take this big fiber, make this fiber flat at a certain position, and make it again balanced. Is there any difference between these two countries? Take a straight fiber, make it balanced. Take the same fiber and flat and make this a small portion of the fiber flatten and make it balanced. Then is there any change in this light which is coming out from this fiber? This we have simulated using console, and you have observed that if there is no flattening of the fiber, as you can see here, there is no flattening. You see, there is no flattening here. Just you have made a value set, maximum light is coming out here. But when you make this flat here, you see, the light is coming out here, and less light is coming out at this output. That means this light which is coming out can be effectively used for refracting in this light. Okay, I want that this light should leak out of this second portion of this optical fiber, where I will put this laserite, and the laserite will interact with this, and will get focus. This is what we have done. So this is what I have said, that you have to play with the geometry of this optical fiber, so that you can know which type of geometry will be suitable for your particular applications.
So which tool is this? FTT?
This is
Which tool is this? FTT or any other tool? Tool simulation. Which
console. This simulation is made at console simulations we are made. Okay. This is another simulation. Again, if you see the simulation, this is not console, this is the real simulation we are made. Here, when you have used this nanometer, you are trying to understand how this light is leaking out, or what is the effect of this size of this nanometer for the light to leak out of this material. That is, you take an optical fiber, for example, and you see what the light which is coming out. Some light is coming out, right? Then we put this nanometer on this optical fiber. And when I say nanometer, then the dimension of the nanometer is maybe 10 nanometer, 20 nanometer, 40 nanometer, like that. Then you vary the size of this nanometer and see what is the effect of the size of the nanometer on the effect on the aberration. That means how this light is leaking out with this dimension of this nanometer. If you see here, we have shown this simulation for different size of this nanometer. These are the different size of this nanometer: 11 nanometer, 16 nanometer, 14 nanometer. So these are the light which is leaking out based on this dimension of this nanometer. And you see this 16 nanometer, the light is coming out, more compared to this other two. It is not necessary that the smaller dimension will give more light. For example, 11 nanometer, the light which is coming out is not more. Similarly, 14 nanometer, the light which is coming out is not more, but 16 nanometer light is coming out. So you have to design this optical fiber, and you have to also design this new materials, standard nanomaterials. So simulation will help you a lot to decide the particular geometry and also to decide the particular size of this number. This is another simulation where we have shown that how light is going inside this optical fiber. You see, what we have got here is this is the core of this optical fiber, and this is the nanometer coating given here. So when you have nanometer coating, what happens is the light, you see here, there's no light is coming out here. The nanometer coating is somewhere here. So when you have given a nanometer coating here, then the light is split into two parts. So the light which is introduced into this optical fiber is now split into two parts due to this nanometer coating, E1 and E2. And when again it is coming out, then the two parts again superposed to be the single light. Now the beauty here. So the beauty is that now I can use this as something like interferometric sensor. For example, you allow this light to divide into two parts. Then you use the magnet here. The magnet will interact with this part of light, and again when you come over here, then these two parts will interfere or superpose to give an interference pattern. And the interference pattern will change with this magnet. So this is something like an interferometric sensor, but in a single optical fiber using a nanometer. So time is actually running out. So just this is another simulation we have made for gold nanoparticles. In fact, let me just complete it quickly. In fact, when we started this research in this optical fiber sensor, we have only a single source, red light source, source. So, but we have an expertise to prepare different nanomaterials. So we try to understand the size of the nanomaterial. What should be the visual size of the nanomaterial? So where you will get this SPM, and based on that, you have to this wavelength of the source. The source if you have, if you have purchased at that time, then change this height of this nanoparticle and simulate it and try to understand what is the best possible size of the nanomaterial, so that it can be used for SPM sensor for that source you had at that time. And interestingly, you have found that if you can make this nanomaterial of 4 nanometer size, then it can give LSPR, not SPR, LSPR for 630 nanometer source. So this is what we have done. Again, firstly, this is the experimental. For the nanomaterial, we prepared the nanomaterials and dynamic characterization. This is experiment, schematic diagram. And finally, these are the different sensors which you have developed in our lab. And I will just take 5 minutes to explain about all these things. In fact, this is a on-flat 300 single fiber. The fiber that we have used is this. This is the nanomaterial which we have used. And this is absorption-based sensor. And this is for refractive index sensing. And this is a on-flat PMMA single fiber. This is the nanomaterial coating which we have given. And this is again an absorption-based sensor. And the measurement is clearly is usually a biomarker for usually cancer. So this is for health monitoring. This is the LOD which we have. Of course, these are the publications where these are published. This is on-flat PMMA single fiber. And the material provided is steam failure quantum dot. This is again an absorption-based sensor. And this is modified on-flat PMMA single fiber. And the material which are coated is glucose chain above non-fiber. And this is based on local surface platform regional sensor. And this is for molecular application. And this is not single on a single water. This is actually hybrid, like a PCF on flat SML PCF. You have to take a PCF and you have to send this on flat SML between two PCF. And this is the nanometric coating, and this is the measurement you have measured. And this is on flat glass fiber. This is the material coating we have used and measure the aceto. And this is value safe human fiber. And this is the nanometric coating we have used for nitrate sensing. And these are the actually LOD sensitivity, and these are the populations where these were reported. So this is all about the different geometries, because as I said, we have to modify the geometry. This is the geometry. This is the material coating. So you have played with this geometry and material coating. You realize different types of fiber for the different. I think this is all about this talk, and if you have any doubts or any queries, then ask.
Any students who have questions to ask?
Wait a moment, students.
First year, someone MSc first year.
Any student who has a question to ask?
MSc students, any questions?